Good morning, good afternoon, good evening, and welcome to my YouTube channel. TESI, a channel dedicated to the theoretical and experimental scientific investigation. Today we're gonna make a very simple video on how to acquire the signal from the linear Hall effect sensor by using a national instrument NI 6009. It's a very interesting data acquisition system, very small and affordable in terms of price. And this is the third part of implementation of data acquisition for the linear Hall effect sensor. We have made already a couple of videos, one where we acquired the signal by using Arduino Mega. The other one by transferring the data from Arduino Mega to MATLAB. I will put those links into the description. But today we're gonna face the acquisition with LabView. So the board is this. Let me get the camera. There you go. This is the NI. I'm gonna put like this. No, I don't want to touch the board because otherwise I risk to remove the connections. Okay, a very small board. The sensor is always this. It's inside. It's inside underneath this green tape. So, by having said that, let's make our connections. We are powering the sensor with 5 volts from national instruments. Arduino provides 4.87 volts, so the values are different, but the main concept remains the same. And then the signal is injected in the channel, the analog channel, in RAC configuration, reference single-ended. It's grounded. So let's open a blank VI. The blank VI substantially is the project that you use the table to draw your circuit. Okay, let's establish to make a while loop. We're gonna make it large like this. We're going input to device assistant, acquire signal. I'm using analog input because the sensor is analog. Voltage. I put the cable in AI, analog input. I put finish. RAC. No scaling. Continuous sample. Alright, that's okay. Now, we have to put. I want to put the video like this first, so you will see what happened in the other part of the channel. There you go, like this. So we're gonna make number of sample to acquire. This is very important. And the rate, the frequency of the resampling frequency. Create, control, perfect. We can make also data, create graphic indicator. Alright, we're gonna put this like this. Remember that the signal acquires from 0 to 5 volt. Those are two values that basically where the signal is in saturation. So to have a better description of the signal, I prefer to make this one a little bit larger, like this, and then put 0 because it will never be negative unless we are not translating the magnetic field. Here we can put 2.6. Let's make 5.5. Auto scaling removed. Alright, it's pretty good now. Play. So signal is at the 2.5. I'm gonna make 5. Alright, and as you can see, I am acquiring the signal. If I get close with the magnet, the same magnet that we have seen in the other videos, right? Where this one is the south pole here, this one, the south pole, and where you see the countersink for the screw head accommodation, right? It's a north pole. I get close to the magnet, and as you can see, it moves. See, I do up and down. So when when the magnet is completely closed, it will reach the value of like 6. Okay, slightly higher than 5. This happens because National Instruments generate a maximum value in output in power supply of 5.25 volt. Arduino generated 4.87. So in the previous video where I have implemented the sensor with the Arduino, if you see that it's lower than 5, it's just because the Arduino is supplying less power. Alright, so by getting close, this is the north pole, sorry, the south pole, and now I flip with the north and it goes down. In the same way, the data sheet of the DRV5055 linear Hall effect sensor states. So after having said that, we are interested also to understand another important property in implementing the acquisition with LabView. You have the possibility to perform the fast Fourier transformation, the graphic one, in real time, and it's very nice actually. So to perform the fast Fourier transformation, first of all we have to consider the signal coming out from the data section, and then use the block spectral. Alright, I want a linear and I want the peak. Ending is fine. I will make some other videos on how to build blocks with National Instruments. Right now this is not the right moment to perform this exercise, but it is very interesting. I start to take some information from these videos, and then we are going to go into depth with the topic. Alright, so now that we have inserted the spectral measurement, we can connect the signal directly to the data output. You can expand and see some other option. I'm not interested in this, but I'm interested in this. Create graphic indicator. The graphic indicator gives you the graphic representation of the fast Fourier transformation. We're gonna scale it, remove it, otherwise it's gonna adapt the Y scale to the maximum peak of the FFT. And now what we're gonna see by pushing play is substantially a straight line starting from this part. Now the signal basically has a certain amplitude, it gets the root mean square, but there is no any harmonic content in this signal. What happens if I get close instead with a magnet and I start to move up and down, right, and I give to the voltage a pattern like a pseudo sinusoidal, pseudo periodical, right? Look at what happened. Up and down, up and down, up and down. You have all the spikes close by. You see that? The little spikes. I will reduce the frequency resolution, which is depending from the sample rate and the number of samples. If I choose 1000 rate, he obviously to create a samples, he has to capture only a value of frequency at the half of the entire sampling, or the entire sampling frequency for the Nyquist theorem. So the signal that I am able to capture with the FFT will be the sample rate divided by 2. If you go over the sample rate divided by 2, you're in coordinate aliasing, which is a phenomenon of the signal alteration due to the incorrect parameterization of the sample frequency. Now, Let's reduce the frequency bandwidth to 20, and let's scale this one like this, auto scale it. All right, like this. All right, let's redo the experiment. Now you see, basically I'm doing an oscillation of 5 Hz, almost 5 Hz, with the signal on the top of the voltage it makes up and down. As a matter of fact, it's a 5 Hz, right? You can count to five waves in 1 second, which is 5 cycles per second. Okay, so very easy, very easy. Let's see what else we can do. So I can try to filter this signal. Let me see. Filter. Let's see if it makes any difference. Butterworth, yes. Cutoff frequency. Let's make 50. We're gonna put a low pass filter. I connect the signal to the data block set and I generate a graph indicator. Oh, instead I want to do something else. I'm not gonna generate. Yes, it's the filtered signal, but I'll remove this one. Right click, delete branch. Right click, remove loose ends. And I'm gonna make instead a unique scope where I inject this signal and this signal to show you just the difference. I remember that there is a block, I think a merge signal, that's right. Let me see if I can do it. Yes, this one and this one. Okay, let's see the difference between the original signal and the filtered one. Play. Let's see. Oh, I had to scale it. Forgot. Okay, let me see. We have a 0, 6. First of all, let's put 6 and 0. I cannot move this window. Okay, wait a second. Okay, let's see. Up and down. Oh, look at the difference. Okay, why the signal filtered is out of phase from the original one? The answer can be done by someone that has always operated with filter or has just like a basic information of how the filter works. We're going to discuss in another video, but let me tell you the reason why it happened. A low pass filter basically is it's a line. Let me open Paint. I'm gonna draw the paint. So the frequency response of a signal, right? It's usually is a line that goes like this and then goes down. If I am removing the content, okay, and I'm saying only this frequency are allowed to be injected on my signal, okay, the other one are removed, and at the same time the phase diagram changes. So all the components are shifted horizontally, okay, because I am attenuating the signal after the 3 decibel per decades. So there is basically an attenuation happening occurring at this point. Okay, so if I remove this frequency content, then my phase changes, and hence the phase of the signal. Just to make the discussion very simple, but I will do also another video on that. Probably will be I will try to explain in a more clear way. But for today, that's enough. If you have any request, anything you would like me to perform, you're more than welcome to call me. Thank you so much, guys. Have a good day. Bye bye.